How's everyone doing? No big complaints, it seems. It's Monday and my brain is not working. Questions before we get started? All right. Well, periodic reminder as we begin here today. Today is Monday the 11th. Main thing we're doing today is beginning chapter 4, talking about force and Newton's laws of motion. And I want to keep on your radar that our first test will be the first week of October, which is to say during that week you will take it during whatever your lab time is. My plan is for us to spend about 2 weeks on chapter 4, just to make sure that it's sound for everybody. And then about another week on chapter 5, which will be about energy and work. And then our first test will be first week of October on chapter 1 through 5. As we get closer to that time, I always post a review guide and a practice test, and spend time in class going over everything, answering questions from you guys. Since tests are given during lab, the lectures during test week are usually focused mainly on on test review, answering questions from students. We'll take it during that week. Then the weekend after is fall break, so you get a nice vacation from physics. And then midterm scores go out on Friday the 13th. Don't read into how ominous that is. Any questions, opinions, concerns, etc. about the calendar upcoming? All right. In that case, on to our main focus for today. Chapter 4, Newton's laws, forces and basic mechanics, excuse me. The past couple of weeks, we've been focusing on the first 3 vectors that we talked about: displacement, velocity, and acceleration. These are what describe motion. Newton's laws, in this chapter, they're going to introduce our 4th vector variable, that being force itself, and look at Newton's laws of motion, which are how Western physics describes what causes motion in the first place. After those first 4, if the first 4 formulas we looked at are the backbone of the course, this is the second backbone of the course. Don't question the biology of that statement. Now, questions before I continue? All right. Now, towards the beginning of the course, I hinted at Newton's laws being pretty important to how physics is done these days. I want to dispel the rumor that Newton invented gravity. One, gravity, things fall regardless of whether or not we do math about it. Second of all, Newton was not actually the first person to do any sort of math or science involving motion, force, or gravity. He is the European that got famous for it, though. But the things that he wrote down are very good, and they are still used today. They are very good formulas that form the background of Western physics for centuries, if I'm being honest. And that's why we still review them today. These statements form, again, the secondary backbone to what I would call Newtonian mechanics, or just mechanics as a whole. Mechanics referring to the motion of macro scale objects that we see and interact with around us on a human scale. And the laws themselves, these 3 individual statements, are all things you've dealt with before. You dealt with these concepts, and I guarantee these laws have been said out loud around you before, so you do know the statements, you do know the things in them. Main thing I want to focus on today is how we're applying them to this course and reminding you what concepts refer to which arbitrary number. Because on tests, I do ask you what are the 3 laws of motion and ask you to number them out of a lineup. You don't necessarily have to have their full text memorized, but you do need to be able to look at a written description and remember which of the 3 numbers it refers to. Does that sound fair? All right. Now, we're going to go over them very briefly here together here at the start. then I'll define a few terms and we'll go into more detail about how we use each one of these in physics. So quick summary of each. Law number 1 says an object at rest stays at rest, and an object in constant motion stays in constant motion unless acted upon by an outside force. Law number 2 does have a full paragraph description of it, but the paragraph is just describing this formula, so very often we just say Newton's second law is this formula. If I ask you what is Newton's second law, you are allowed to just write this. You are allowed to just say FMA. The law says net force equals mass times acceleration. If you exert force on an object, it will accelerate. And lastly, the third law, which is the one that gets quoted and misquoted the most in my experience. For every action force, there is an equal and opposite reaction force. These statements sound familiar. Good. Now, before we use these in detail, I want to define our terms. Make sure you have written in your notes the official definition of a few things. I did say at the beginning of the course, whenever I bring up a new variable, a new thing to measure and calculate, I will always tell you what it is, how we measure it, what it's measured in, etc. So first, since these laws all have something to do with the concept of force, let us quickly review the physics definition of force and how we use it in here. The definition of force, actually skip a few lines, is a push or a pull that acts on objects with mass to create acceleration. It's a fairly straightforward definition. It's a new variable, it's on your formula sheet, and any formula that has it will have a capital F to stand for it. So capital F will always stand for force in your formulas in this class. Force is a vector. It's important to know about it. Force is a vector because every time you've ever pushed or pulled anything, that has been in a direction. Do you concur? You cannot push something without pushing it in a direction. Does that sound all right? So, force is a vector. It's very important. We are going to measure force in units of newtons in this class. Newtons is the metric unit of force, named after Isaac himself. But in the United States, we commonly use pounds as an alternative to newtons. So whatever you normally measure in pounds in your day-to-day life, including but not limited to weight, pounds per square inch in reference to pressure, punching force. I watched a lot of Mythbusters. They did a lot of punching and explosive yield measurements in pounds. Can be measured in newtons. So same difference between feet and meters, basically. For a sense of scale, if you're not used to thinking in newtons, 1 pound is about 4.45 newtons. So if you take your weight in pounds and multiply it by 4.45, you will get your weight in newtons. For a secondary sense of scale, average human adult male weighs about 1,000 newtons. Summary sound good so far? All right. Now, within this definition, I mentioned mass, so we want to make sure to define mass as well, since I don't think I've done that. Mass is the amount of matter inside of an object. It is not a vector. Mass does not have a direction that you have to worry about. You can push mass in a direction, but the mass itself never inherently points anywhere. Mass is a scalar. It is abbreviated to lowercase m in all of your formulas, always lowercase. Uppercase m means something else. We are going to measure mass in kilograms. Usually, if one is using the metric system, your formulas tend to use the base unit without a prefix, and that is true of other disciplines like chemistry in this case. But in physics, for complicated historical reasons, we use kilograms instead of grams. Anytime you see a mass in your formula, I want you and the formula wants you to plug kilograms into it instead of grams. Historically speaking, I believe the reason that physicists do this is to keep all of our numbers smaller, whereas chemists and biologists are usually working with very small samples of cells and piles of dust. Physicists tend to work on a slightly bigger scale most of the time, even if you're not doing astrophysics. If you're thinking about people and animals and cars and trees, the scale of that is usually better thought of in kilograms than grams. Human mass, for example, might be somewhere between 50 to 150 kilograms. If you used grams, those numbers would be 1,000 times bigger, and so too would all your calculations. So I believe historically physicists chose kilograms just to keep all the units smaller. And that's why we continue doing that to this day. If you use grams, your work won't work out right, because the very definition of 1 Newton of force is the force needed to accelerate a 1 kilogram object at 1 meter per second squared. Physics has based its foundation on kilograms over grams, and I'm going to be trying to help train you guys to auto-correct and can auto-convert grams to kilograms whenever you see them in a question. Sound okay so far? All right. Last quick thing that I'll talk more about later. Mass is not the same thing as weight. Mass is the matter inside of an object, and weight is the force of gravity. Mass is measured in kilograms, force and weight is measured in newtons. I don't care how much British television you watch, kilograms is not technically a measure of weight. Because mass doesn't change if you go to the moon, but weight does. Make sense? Okay. That is just something I get annoyed at whenever I watch Top Gear. It's not super important, but I'll remind you as we continue talking about how gravity works. Definitions sound okay so far? All right. With those defined, let's look back at the laws and talk about how we use them in this class. The first law, if I was to, as I go through each one, I'm going to give a summary or a name for each one. The name for the first law is the law of inertia. It refers to the inertia, the innate tendency of motion of an object. So if you've heard the word inertia before, perhaps in the Bill Nye theme song, this is the statement it is referring to. And if I was to give a very quick summary of this law, it would be matter is lazy. Whatever matter is currently doing, it wants to keep doing it indefinitely. And to make it change, you literally have to force it to change. I will elaborate. Behold, matter. You may be impressed. I have here a lump of carbon atoms for the most part, and I'm just going to place them right here. What are they doing? This is not a trick.
Staying still.
Staying still. This mass is currently at rest, and do you assume it will remain at rest indefinitely? It actually will. If nothing else changes about the equilibrium of this system, that remote will stay there forever. For that remote to not be at rest, something outside of the remote has to change and exert force on it. But if everything stays even from now until the heat death of the universe, it's just going to stay there. Objects at rest stay at rest because matter is lazy. Whatever it's doing, it wants to keep doing it forever. That remote will not spontaneously leap off the table unless something makes it do that from outside of itself. The same is still even true for your human body, because you are not one object. You are a bunch of objects stapled together inside of a skin sack. So whenever you move, that is your muscles exerting force on your skeleton and the rest of you. That is a force from outside of your bones. Objects at rest stay at rest until literally something forces it to change. If you're staying still, you'll remain that way until the equilibrium is broken. Even if that thing does suddenly fall off the table, it's because the equilibrium of the table was broken by something, like the table moving beneath it. How does that feel so far? All right, so that is part one of the matter is lazy explanation. Part two of the matter's lazy explanation is the objects at constant motion remain in constant motion part. Because not only do stationary objects want to remain stationary, objects that are moving want to keep moving. If you're driving a car and you take your foot off of the accelerator, what does the car do?
Slow down.
It keeps going forward, and that's because its own inertia tendencies tell it you're moving, keep moving, don't change anything. It does eventually slow down, but that's not because the car wants to slow down, that's because friction from outside the car forces it to over time. It wants to keep going, and that's why it doesn't just immediately halt the second you take your foot off the gas. Sound okay so far? Okay. All matter, if in motion, wants to remain in motion. You kind of have a hard time measuring that on Earth, though, because on Earth we have this pesky thing called friction, and it is everywhere. And friction is literally opposing every single motion you will ever make. When driving a car, if you take your foot off of the accelerator, there is now no longer any force pushing the car forwards. Instead, there is a bunch of forces pushing the car backwards. Friction from the tires, the ground on the tires, friction from the air on the chassis. All those backwards pointing forces over time accelerate the car from 60 to 0. But the car wants to move forward, and if friction didn't exist, it would just keep going. This is why cruise control exists. Cruise control is a function of your car's computer brain that calculates just the barest minimum amount of required force to keep moving forwards and overcome that backwards pointing friction. Your car wants to go forwards, cruise control just overcomes the friction that tries to stop it. All matter, if in constant motion, wants to stay that way. Hard to see it on planet Earth, but if you leave the planet, you start to see it more often. Right now, as we speak, above planet Earth, there is tons of random little space debris like bolts and screws that flew off of satellites constantly orbiting the Earth that will never stop. These bolts and screws and panels, what have you, flew off of exploding satellites because sometimes they crash into each other, sometimes meteors hit them. All those little pieces of trash have a velocity, and their innate inertia says keep moving at that velocity until something stops you. And up there, there's nothing to stop you. There's no wind. As long as you keep moving, gravity will keep you in orbit so you don't run into anything. So unless you physically fly into another object, or if your orbit decays, you burn up on re-entry. Until one of those two things happens, all that trash just stays there forever. And if you really want to see something go indefinitely, instead of orbiting the planet, just throw it further away from the planet. If you chuck something into the infinite void of space, it will go forever because there's nothing to stop it. That's why Earth keeps moving through space. It's why comets keep going and come back eventually, but they keep going on their own. Objects in motion stay in motion. And in space, there's nothing to stop you. There's a semi-famous quote from the game Mass Effect 2. Isaac Newton is the deadliest man in space. Because if you throw something in space, it'll hit something eventually. May not have been your original target, but you'll kill something. So, matter is lazy. It's going to keep doing whatever it's doing until something forces it to stop. It'll stay still until something else forces it to change. It'll keep moving until likely friction makes it stop. That's kind of why friction is a big pest. We'd have perpetual motion if it weren't for friction. Sound good so far? Questions, concerns? All right. On to Law 2, which arguably is the most useful given that it's a formula, and we like formulas in here. Net force equals mass times acceleration. I'm going to compare this back to the previous law real quick, so that we can put some numbers to the previous law. What this says is, if an object is not accelerating, the net force is 0. you see here in the formula, if A is 0, it doesn't matter what M is, net force is 0. Which likewise means, if you're not acting on something, its acceleration is 0, and it's going to keep doing what it's doing already forever. My remote, net force is 0, it doesn't accelerate, it doesn't start moving. Meteors in space, net force is 0, acceleration is 0, they keep moving at the same velocity in a straight enough line forever. So that is how the first law turns into the second law in terms of the math. So if F equals 0, A equals 0, and vice versa. Feel okay so far? Okay. Now I actually learned this law not from a science teacher, but from my Taekwondo instructor as a kid. So I'm gonna probably often refer back to that stage of my life as fodder for creating physics examples. The way my instructor taught me this law was by saying, if you want to punch something harder, you either need a bigger fist or you need to move your fist faster. The way the math here works, if you exert force on mass, it accelerates. The more force, the more it accelerates. The bigger the object, the more force you need. This is why it's easier to hit a baseball with a baseball bat than a bowling ball. Bowling ball has more mass, requires more force to get moving. Likewise, that's why trains are very hard to stop. They have a lot of mass, requires a lot of force to decelerate them. So this formula just summarizes the numerical relationship between all those things. And a couple small quirks. I want to point out both the F and the A here are vectors. Mass is not a vector. Mass is a scalar, mass doesn't point anywhere, but the A and the F are vectors. And they're both vectors that have the same direction because one informs the other. If I push something east, it accelerates east. The acceleration inherits the direction of the force. Sound okay? All right. Other thing I want to point out is the big old letter sigma on the front. That's not there for decoration. It's here for a reason. It's net force equals mass times acceleration. I'm going to draw your attention again to my brick of carbon of science. What are the forces currently acting on this object?
Gravity and the force supported by the table that is keeping it up.
Very good. Those are two very specific forces. I am going to represent them visually using something called a free body diagram. This is just a fancy way of saying I'm going to draw a box and put arrows on it representing the forces. And they're always boxes because not a lot of physicists are very good artists. So, behold, the remote is a box, 50 grams, just as a sample number. And as you said, gravity from the Earth points down, and some force from the table supporting the remote is going to point up. This is true of anything that sits on anything else. This is true of you and your chairs right now. The chair is pushing up and supporting you. So there are at least two different forces acting on that remote, and separately, neither of them is zero. Because if they were zero, they wouldn't be there. There are forces here that aren't zero. So if there's forces here that aren't zero, shouldn't the remote's mass be accelerating? Technically, yes, if those forces were imbalanced. So again, the formula says net force, the vector sum of all the forces present. Sigma always means net, net meaning summation of, S-U-M of. The definition, oh, I forgot, I made a slide for this. Sigma F means net force, sum of all the forces, vector sum, S-U-M. Literally, it's not just any single force, it's all of them added together. So in the case of that remote, gravity pulls down, the table pushes up, and I know from experience, because that remote is currently stationary, these two things add up to 0. And if net force is 0, specifically if net force is 0, acceleration is 0. Separately, there are at least 2 different non-zero forces, but they add up to 0. And the net force is what determines overall final net acceleration. Single forces on their own mean nothing without the context of all the others acting on the same object. Is that a thumbs up or just your pen hand? Okay. Now, there's not really a different formula for net force. Net anything, sigma anything, is always the sum of all of that thing. So for net force, I would say find all the forces on an object and physically add them together. But because force is a vector, you do have to note x versus y, and also positive or negative within that axis. In the case of this remote, again, whatever gravity is pointing down, I'll just, I know what it would be. I'm just gonna round it to 1 Newton. No, it'd be 5 Newtons. No, 0.5 Newtons. Separately, they're not 0, but because they point in opposite directions, when you add up the vectors, it becomes 0. This is true for any object in equilibrium that is not currently accelerating. Doesn't matter how many forces are involved, if they add up to 0, acceleration is 0. And that is how equilibrium is created. You are all, from our frame of reference, in equilibrium right now in your chairs, because the same thing is happening to you. Gravity down, surface pushing up. They add up to 0, you remain in your chair. You do not accelerate through or out of your chair.
There's an equation for force of gravity, correct?
There is, yes. Force of gravity is equal to the object's mass in kilograms times the acceleration of gravity we talked about previously. So mass in kilograms times negative 9.8 meters per second squared. There's going to be a lot of different types of force in this class. All forces still act as forces. They still push or pull on things, and we still measure them in newtons. But force can come from a lot of different places, and as a result, individual forces often have different names and labels. For example, within this one picture, I've got Fg, F with a subscript of G as a label for force of gravity, which, again, is a direct synonym to weight. And it's going to be commonly what I use as the symbol for gravity in this class, because gravity is a force. It's important to remember that. So F subscript G is force of gravity. Likewise, up here, this arrow pointing up represents the supportive force from the table pointing up on the remote, and that is, again, the force that keeps the remote from just falling through the desk. Algebraically, we call that normal force, and so often it'll be abbreviated as Fn, but some people just call it N. In fact, your formula sheet may use just capital N for it in several places. But F subscript N or capital N refers to normal force. It's just a specific source for force. And to very briefly address why it's called that, why it's called normal force. It's not using the standard definition of normal, meaning typical or common. It's using the math definition of normal. And in math, normal is a synonym for perpendicular. Math normal means this table is oriented horizontally, yet the force it's exerting on the remote points vertically. All surfaces can create normal force. When you push into something, it pushes back out, which is actually a function of Newton's third law. Just skip ahead briefly. The table pushes back on the remote because the remote is pushing into it. So that's how third law ties into this. Because the remote is pushing perpendicularly into the table pushes perpendicularly back out on the remote. Normal force is always perpendicular to the surface that creates it, and that's where the name comes from. You do not have to memorize or make sense of that yet. We'll do a full dive on it as the week goes on.
So right now, we're only, whenever it comes to force of gravity, we should only focus on force of gravity by Earth.
Yes. I will always tell you if something doesn't happen on Earth. If a question does not specify, on another planet, you can assume something's on Earth, which makes this automatically true.
Okay. And that's just weight. G is weight in kilograms?
Hold on. I'm going to rewrite this. F subscript G is weight. That's not F times G, that's F with a subscript. And that's equal to mass in kilograms times negative 9.8 meters per second squared.
Okay, that's good.
And that's because the force of gravity causes the acceleration of gravity, meaning that when I let go of something, the force of gravity pulls down on it and causes this acceleration. So the weight of an object is always enough force to accelerate its mass at this rate on Earth. Again, there's lots of different types of force, and we're going to spend the rest of the week looking at the different types, talking about how they come up, how we calculate them, what they're used for, etc. So I wrote this list here to give examples of the many subscripts. We're going to talk about each one in detail as we go. Does that sound okay? All right. Main point for right now. There are multiple forces on that remote that currently add up to 0, and that is why it is not accelerating. And that is true for everything you've ever interacted with your entire life. There is not a situation in this universe where there is not force acting on something. There will always be force acting on your body, because even if you leave Earth, you're still in the same universe as Earth, and the gravity of Earth doesn't shut off even when you get far away from it, it just gets weaker. Technically, I could calculate the gravitational pull from Pluto on my body right now. It exists, it's just super tiny, because it's very far away. But it's there, and it's currently adding up to and canceling out with every other force acting on my body, from Earth, the floor, your gravity, the Andromeda system, etc. So there's always forces on everything. We mostly just care about the big ones and how they all add up to 0. But there will always be force acting on every object you ever see, including your own body. Even in space. There is gravity in space. You do not turn off gravity by leaving planet, I promise you. There is gravity in space. Questions thus far? Okay, so in reference to this formula again, if net force is 0, you don't have acceleration. If the forces are imbalanced, that is what causes acceleration. And that is again why this thing remains in place until I literally force it to change. My outside force is not balanced out by any existing force present. And so that imbalanced force causes the remote to accelerate. And as a result, we'll be using this formula very commonly. But it's specifically net force. Cool? All right. Law 3 comes up the least out of them, but it's important to know when it comes up. Again, it gets quoted and misquoted very often. I'll just remind you now, for every force there is an equal and opposite force, which means whenever object A acts on object B always acts back on object A with the same force in the opposite direction. That is true for literally every single force that ever occurs. It's even true of gravity, weirdly, but we'll talk about that later. Any force interaction causes an opposite to occur. If I lean against the board I exert force on the board, therefore the board exerts a force back on me, and that's why I don't fall over when I do this. If the remote pushes into the table pushes back up, and as long as the table can handle all of those forces, the remote remains in place and the table doesn't break. Interesting things happen if you do exert enough force to break something. Namely, most objects have a certain maximum threshold of force they can exert back, and if you exceed that maximum, it breaks. For example, if instead of a remote, I put an anvil on this desk, anvil weighs 2,000 newtons, table can exert 1,000 newtons. The table will exert the 1,000 back until it snaps, and then because the system's in balance, the anvil accelerates through the broken table. So the anvil isn't in equilibrium, therefore it accelerates through the broken table. So when things break, the reaction force just isn't enough. But if the reaction force is enough, well, if you're punching something, that's why you hurt yourself after the fact. I exert force on thing exerts force back, and then my knuckles hurt. Again, I'll talk more about this as it comes up in specific cases, but it's where this desk upward force comes from. Questions thus far? Okay. I've done a lot of talking and hand waving today, so let's end with a little bit of practical math, just a little bit, to apply these things and get in your notes before we leave for the day. First question. Using a baseball bat, you strike a 50-gram baseball with a force of 100 newtons. What will the ball's resulting acceleration be? I will put a picture and all the numbers on the board. I would like to know what you guys calculate.
Mass is measured by kilograms, so we'll have to convert to grams.
Excellent catch. That force equals ma. Our applied force will be the net force here because there's nothing counteracting it. And before we actually plug mass in here, yes, we like kilograms. How many kilograms is 50 grams? Say it again.
0.05.
Very good. 0.05. This is effectively dividing by 1,000, or visually speaking, dragging the decimal point 3 spots to the left. Again, anytime you see grams, perform that to get kilograms before you use it in anything. So with that done, 100 newtons equals 0.05 times A. So we're going to be dividing by a tiny number. And as a result, big force on very small object creates very big acceleration. Which is just the essence of Newton's second law. Big force, small mass, big acceleration. Now this may not be actually to scale with human baseball players. I probably got the mass of a baseball wrong.
It's
Because
also a stationary ball.
Hmm?
It's also a stationary ball.
That is true, That is true. The acceleration would have less of an effect if it was having to change directions first. So good observation. I didn't take that into account either. But forces that big, if applied long enough, the baseball could break Mach 1. So I did probably get the mass of the ball wrong.
Wait, in meters second squared, what's Mach 1?
Mach 1 is 343 meters per second.
That ball's gonna be scorched.
Yeah. If that bat was in contact with the ball for 1/6 of a second and it was starting at rest, it would crack Mach 1. So I'm going to assume the Hulk is on this team. That's a small fact about collisions. They all take an amount of time for the acceleration to occur. So that may be an average amount of force, but a baseball is only touching the bat for a fraction of a second. Feel okay there? Main thing to note is, again, kilograms. All right. Next one, instead of a baseball, we've got a car. 2,000 kilograms is fairly average for a vehicle, somewhere between a sedan and a truck.
We're gonna have to convert, well, not convert, we have velocity, and that's not acceleration.
Right. So what I listed there is velocity of 30 meters per second.
Since it's constant, wouldn't the acceleration be zero?
Correct.
So the force would be zero?
Yeah.
Constant velocity means acceleration of 0. So velocity is 30. The acceleration is 0 because of that word constant. And I can prove that. If I use formula number 2, A equals delta V over delta T. Question says that 30 meters per second is constant, meaning it doesn't change. So if the final speed is the same as the initial speed, delta V is 0, therefore A is 0. And if A is 0, doesn't matter how big the truck is, net force is 0. So once again, if you are not accelerating for any reason, net force is 0. Now, are there separate non-zero forces on the truck? Yes, there's always forces acting on everything because you cannot escape gravity at minimum. So I'm going to make another small free body diagram here. Again, just a fancy term for box with arrows. What are the forces acting on this vehicle off the top of your head as it's driving along?
Friction of wind.
All right. Assuming this way is forward, friction would point backwards. So I'm going to call that FF for force of friction.
Yeah, normal.
Very good. The road's going to push up like it did for the remote.
And gravity.
Very good. Gravity keeps you from flying away from the planet. Normal force keeps you from sinking into the ground. So we got at least 3. Now, if the net force is 0, that means all of these need to add up to 0. And it's reasonable to assume that the normal force and the gravity tend to cancel out on flat surfaces. But that means that something here has to be canceling out the force of friction.
The acceleration.
Yeah. Well, air is causing the friction, at least in part. The air and the road are trying to slow you down because you are moving over the road and moving through the air. And matter doesn't like when you move over it or through it. So friction happens because matter slows you down. In order for this car to keep moving at constant velocity, there has to be some amount of applied force forward. So I'm just going to call that force applied for now. Realistically, this would be the driver just barely pushing down the accelerator to create enough force to counteract friction. Again, cruise control does that for you automatically. So if cruise control is on, the engine is doing something. It's creating just enough force to negate friction and keep you at the same speed. And it is only when all of those forces add up to zero that you remain at constant speed. It's just the vents. For some reason, colleges always put the physics department in places without windows. So at other schools, we would have to play our favorite game, rain or vent, every time we heard that noise. But given that this is the basement, it's always the vent.
I was fun of the game.
Hmm?
I was fun of the game then.
It really isn't. That said, at least it makes this room tornado proof. Question? Or,
I was just saying, yeah.
yeah, sorry. Again, every hand motion, I've conditioned myself to think question, squirrel. Okay, so for this one, despite a velocity, it is constant, therefore acceleration is zero, therefore that force is zero. This car is in equilibrium, all four forces add up to zero. If any one of these was bigger than its directional counterpart, you'd get an acceleration. If gravity was bigger than normal force, you'd sink into the earth. If normal force was bigger than gravity, you'd jump upwards. If friction is bigger than your applied forward force, you slow down. If your applied forward force is bigger than friction, you speed up. And as the week goes on, we'll continue defining all these types of force, where they show up, and calculating more specific scenarios. How do you guys feel so far? Yes?
I was wondering what our first test or assignment.
The 6th?
Possibly the 6th, depending on when you have lab. It'll be the first week of October. It happens during lab period.
Oh, so it's session.
Okay. So if I have lab on Monday, then I'll have on Monday.
Yeah. Now that said, it's still like lab. You can attend a different section if you want to.
Oh.
Some people all come in on Friday because they want more time to study. Some people come in on Monday because they just want it over with. Either way, I have study sessions during the week to make sure everyone's ready. And it's a month ahead. You're going to be ready.
Because we're just covering this chapter and.
Yeah, we got 4 and 5, then time to review, then the test. So 4 is about force and Newton's laws, 5 is about energy and work, then review, then the test.
Okay.
Sound good?
Got it. Yeah.
Questions, concerns, objections, haiku? All right, in that case, we'll call it here for today. Have a nice Monday. Let me know if you need anything. Come to lab as normal. Oh, sorry. Unrelated question. It's not a big deal. I just would like a show of hands of anyone who plans to also take 1510 in the spring. If you are planning on taking Physics 1510 in the spring semester. Okay, thank you. That is all. The department just wants to have a wonderful day.
See, I have a lot of science.
Sorry.
Shit. And I have no clue if they're going to be.